Jadi nggak usah, misalnya unformal kita-kita aja gitu. Nggak usah, oh, nah harus formal pakai ini ya. Kita-kita aja punya ide gagasan tetapi atas sepengetahuan pimpinan gitu.
Iya, kalau dilihat dari perkembangan ini kan memang si La Nina-nya masih bertahan. Yang menarik malah ini SST-nya juga bertahan juga sampai periode kemarau nanti.
Nah itu
Maka ya statement awal sementara kita yang menyatakan bahwa onset-nya akan mundur saja dulu untuk yang awal kemarau kita. Nah, kalau kita nggak terlalu ngangkat yang akan above normal ini selama periode kemarau, takutnya publik menganggap bahwa nanti kemarau basah ini
wah,
seolah-olah tidak
curang.
ada musim kemarau. Karena
Ada,
tergantung membahasakan.
ada.
Makanya takut membahasakan kalau atas normalnya di periode kemarau ini dianggap sebagai
Andaikan.
dry season period.
Ini aku berandai-andai nih. Andaikan. Ini andaikan ya, andaikan gitu ya. Musim basahnya nih hujannya berlanjut hingga Mei. Padahal kan bulan puasa bulan pembakaran dosa ya. Biasanya kemarau tuh. Ini hadisnya yang salah atau data lo yang salah? Baca dong hadisnya. Setiap bulan Ramadan itu kemarau. Kenapa? Karena ada pembakaran dosa. Panasin dulu. Soal nanti menjadi hujan lagi itu soal nanti. Tapi kalau begini kan kondisinya, ini hadisnya perlu dipertanyakan nih, sohe nggak nih? Ya,
Alright.
canda-canda.
Selamat sore Bapak Ibu semuanya.
Wah,
Selamat.
nih Pak Moderator.
Oke, ini dia Pak Moderator.
Pak Moderator
Oke.
sudah hadir.
Ngomongnya di session ini ada orang bulenya nggak sih?
Ya, English kayaknya.
Ya, English. Alright.
Eh,
Ada satu orang Bapak.
Sopo?
Paul Davis.
All
Mr.
there
Paul
is.
Davis. Alright.
Ya, kalau
Sorry. Simon Pittman. Simon Pittman.
ya udah enggak, maksudnya 1 lawan 7 ya kalah lah satu. Lebih jelas gitu.
Ya.
Nggak apa-apa sih.
Oke, so jadi kita sepakati saja in English mungkin ya Bapak ya, karena
Oh iya.
ada dari native. Alright, good afternoon, ladies and gentlemen. Welcome here.
Udah mulai gitu?
Ini
Dicek.
just I think we will check the presenter first
Iya.
and the conference, and after that we can start.
Kaget akunya.
And first of all, maybe I will check from the presenter. So based on the schedule, the first one is Mr. Harrison Primadonna. Are you there? I think Mr. Harrison is not already here.
I'm here.
Oh, thank you very much, Mr. Harrison. And for the next one, we have Mr. Adi Ripaldi. And good afternoon, Mr.
Yes, good afternoon.
Yeah,
Amir.
have a nice day. And the next one is Mr. Simon Pittman. Are you here?
Yes, hello,
Mr.
can you hear me?
Okay, so are you in Leeds? So I think, yeah, still in the morning in there.
It is, yes, it's 9 o'clock in the morning.
All right, yeah. Have a nice day. We will check another one. Okay, after that we have Alif Nabilatur from ITB.
Yes. Yes.
All right. And the next one is Rigita Putri. You can speak in here for check the sounds. And Rigita Putri Damayanti. Rigita, okay, I think still not here. And so we will move to Firas Rashid. Mr. Firas?
Yes, I'm here.
Okay, thank you very much for the confirmations. And then the last one is Devi Fatmasari from BMKG. Miss Devi?
Yes, I'm here.
All right, so we just lost one presenter. And I think we can just start now because the time is up and we have a little bit late from the plenary session. So I think we can start the oral presentation now. So welcome here, the Honorable of the Controller, Professor Dr. Eddie Hermawan and Dr. Kunio Yoneyama. Are you here, Mr. Eddie is already here.
Yeah, I'm here. Nice to meet you again, all participants. Welcome to the session.
Thank you very much, Mr. Prof. Ed. And the next one, for the convener, we have Dr. Kuneyama. Isn't already here? I think not really. Hello, Dr. Kunio Yoneyama. Are you have been here? I'm not really sure. I think Dr. Kuneyama is still not here. Yeah, so we can start now because we have the convener here, and maybe we will waiting the Dr. Kuneyama and just start the presentations. Is it all right, Prof. Eddie?
For me?
Yeah, all right. Should we have wait for Dr. Kuneyama?
Okay, ladies and gentlemen, good afternoon for all of you. Welcome to this important session. We talk in the basic science, and here we have how many?
Seven presenter here.
Seven presenter. We would like to see what you have done, what is the important point you will be talk in this session. And now still we are waiting for the Dr. Yoneyama. Maybe we should ask him in Japanese. Yoneyama-san, imasenka? Sorry. I hope you all can give best your presentation with good motivation and good result of then we hope you can make presentation at in time 10 minutes or 12 minutes, and then this session will be lead by Dr. Amir Mustafa from BMKG, and please enjoy this afternoon meeting in this session, and hopefully we can find some nice, interesting point result of the, then we hope you can give the best what you have done, your study, your result, your whatever you are doing now. This is a important meeting. It's a good chance for you all to present what you have done, your works. Please enjoy again. Please keep your spirit, and we will see what is the best from all of you, your result, your presentation, your answer, and etc. Welcome to this this session, basic science, and to the moderator, I will give you your time now. Thank you very much for your attention. Thank you.
All right, thank you very much, Prof. Eddie, for the opening speech before we start the presentation in here. And for the first one, I will just explain a brief rule for the presentation here. So we have 7 presenters, and first of all, I will introduce myself. My name is Amir Mustafa Irawan, and I'm from STMKG, the School of Meteorology, Climatology, and Geophysics. And here I'm a moderator to the presentations. And so we have 7 presenters, and for the rules, I will divide it in the 2 sections. The first sections there will be 3 presenters that will present their results. So the first sections, it should be for the Mr. Harrison, Mr. Adi Ripaldi, and Mr. Simon Pittman. And the time allocation for each presenter is 10 minutes. So as Prof. Eddie explained before, is 10 minutes. And the total time, it should be 30 minutes for 3 presenters in the section 1. And after that, we will develop a discussion. And the time for the discussion is 2 minutes for one person. So the total is 6 minutes. So in the section 1, we will have 3 presenters. And after that, we will develop the discussion in 6 minutes. And after that, we will go to the section 2 that will be the next sections for 4 presenters. That is for Arif, Mr. Arif, Ms. Ringgita, Mr. Firas, yeah, and Devi, Ms. Devi. And same with the section 1, you will have 10 minutes for the presentations and 2 minutes for the discussion, but the discussion will be conducted in the last, after the 4 presenters. So in the total for discussion is 8 minutes. And that is the rules. And after that, we will, I will move to the convener. So the convener will give feedback and comment for improving the presenter material or the research material, so that we can just develop the best research for you all. Thank you very much. And just for remembering for the conference of edit, don't forget to give a score for each presenter in the form that this committee provided. Are you received the form, Prof. Eddie?
Yes, but please, I would like to sleep now. Oh, no. It is my job. Please believe me, okay?
That's fine. Yeah. Thank you very much for the response. All right. So we will just start from the presentation from the presenter 1. That is Harrison Primadonna. You have 10 minutes for present your research, and so the presentation is like near with the finish, like just 1 or 2 minutes left. I will give warning to you, so you can just ending your presentation in the time manner. Thank you very much. So we please welcome to the first presenter, Mr. Harrison Primadonna. Time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thanks to the moderator for taking the time to present my research. Okay, my research title is The Effect of MGO on Cloud Vertical Structure in Sumatra from Radio Sunday Observation during GPA1 and GPA2 conference. And myself, Harrison Primadonna, together with Mr. Marzuki, Mr. Muhammad Ali Shafi'i, and Professor Hashiguchi from Kyoto University. We can see from the title, the focus of the study is on the effect of MGO. As we know, that MGO is one of the dominant oscillation in the tropic, which move from west to east along the equator. MGO affect almost all weather parameters such as wind, humidity, temperature, rainfall, and clouds. So it is important to learn especially in relation to clouds. Talks about clouds. Clouds influence the atmospheric circulation, the Earth's hydrological cycle, and the energy budget. One of the main things affecting it all is the vertical structure of the clouds, because clouds have different physical properties depending on the vertical structure of the cloud. Therefore, high clouds tend to warm the surface by absorbing long-wave radiation, while low cloud tends to cool the surface by reflecting solar radiation. And therefore, the vertical profile of latent heat and radiation from a cloud is determined by the cloud vertical structure. Thus, knowledge of cloud vertical structure is essential for increasing understanding of atmospheric circulation. Cloud vertical structure study is very limited in Indonesia. Some studies mainly deal with spatial or horizontal distribution of clouds. For example, Marzuki et al. 2013 and 2017. This is the result Marzuki et al. 2017. My research, this work is follow-up of Marzuki et al. 2017. Investigation cloud vertical structure during 2 periods of coupling process in the equatorial atmosphere, namely CP1 April to May 2004 and CP2 November to December 2000. Next. So in simple terms, the data used this study is the humidity data for CP1 and CP2, which we can download from this website. Then the vertical structure of the cloud is calculated using the Zhang methods, 2018. This method established several moisture thresholds to determine cloud top, cloud base, and cloud thickness. This is the threshold used, taken from the journal Atmosphere Chemical Physics, 2008. This is an example of calculating the vertical structure parameter of a cloud. So we can see that this is 1 layer, 2 layer, 3 layer, 4 layer, and 5th layer. and so from here, we can see that the black line, there is a relative humidity with water, and red line, there is relative humidity with ice. So we need to do a conversion from relative humidity of water to relative humidity of ice, especially for height above 0 degrees. So since we are researching about the effect of MGO, we need to know the phase of MGO during GPA1 and GPA2. So here we take the MGO index of the Australian Meteorology Agency website. There is con and the percentage of cloud occurrence during GPA1 and GPA2 convent. Total of launch radius is 160 236 and 216. And we get French attack, 1 layer, 2 layer, and 3 layer have French attack slightly higher than GPA2. We can see. And different for layer and more than 4 layer. And the cloud occurrence percentage for all numbers of the layer was slightly higher during GPA1 when an active MGO event occurs, except for all cloud with more than 3 layers. This result for structural vertical clouds for 1 layer. We can see during GPA1, average for cloud top, cloud base height, and cloud thickness. And during GPA2, average cloud top, cloud base height, and cloud thickness. This is during GPA1 slightly higher than GPA2.
Your time is 2 minutes left, Mr. Harrison. Thank you.
You can see cloud top is different. And for 1 layer, there is active MGO and active MGO. During an active MGO, average cloud top and active slightly higher during active MGO. There is value close by height and cloud thickness. For cloud vertical 2 layers, we can see during GPA1 average cloud top slightly higher than during GPA2 average cloud top. We can see, but different for second layer. You can see, and during MGO active and active for this layer, this value is slightly higher than MGO inactive, slightly higher than MGO active. This is similar to for 3 layers. Okay, in conclusion, the heuristic defines the percentage of cloud inference in GPA1 where MGO active is observed is slightly higher than GPA2, with as the weak MGO phase. The influence of MGO is strongest in single layer and first layer of multi-layer clouds. The cloud stop in the test clouds are higher in the inactive phase of MGO than in the active phase of MGO. Future work clouds also have diurnal variation, and this is being studied, and the result will be published in another paper. Thank you, moderator. We can back to moderator.
All right, thank you very much, Mr. Harrison, for the nice presentations. So before we move to the next presenter, I will remembering the audience, if you have any questions to the presenter, you can just drop your question in the chat box here. Yeah, so we will discuss it in the discussion sections. All right. Okay, so we will move to the presenter 2, Mr. Adi Ripaldi. Please welcome Mr. Adi Ripaldi. Time is yours.
Thank you, Mr. Chairman. Sorry, Mr. Horizon, could you please to, yes, also my presentation. Can you see my presentation clearly?
Yes, it's clear.
Thank you, Mr. Chairman. Good afternoon and good morning for some participant in another Indonesian, maybe in Japan or some country. Here I'm Adi Ripaldi from BMKG, Central for Climate Change. My team with Pak Dodi, Andika, Robi, and Rosi Hanif, and also some author from BPPT and also from University of Indonesia. We will be to presented about the evolution of a sea temperature anomaly in 3.4 region into Indonesia rainfall anomaly during the El Nino 2015 and 16. As a background, we will see that the in 2015 El Nino has declared as the biggest or the strongest El Nino. That some people say that 2015 is the Godzilla El Nino. And we know that there are three times the strong El Nino: 18.2 to 18.3, 97 to 98, and 2015 and 2016. And here in my assessment, I will be looking for the comparison between the strong El Nino 97, 98 to 2015 and 2016. The impact of the El Nino, we know that for Indonesia, when the El Nino coming, it will be long dry season, forest fire, haze, and also some drought condition in some area in Indonesia. And in here we will know how the impact of the El Nino 2015 is more severe than El Nino 97. We will see with the result. What interesting in here, we will see how the evolution of the East anomaly and general wind over the Nino 3.4 and SST anomaly over the maritime continent during the El Nino, and how the El Nino impact for Indonesia rainfall. Variability, particularly the El Nino impact in 97 compared with the 2015. And the output, we will get the assessment, the comparison, the SST changing, general wind over the Nino 3.4, SST anomaly maritime continent during the El Nino, and the impact for our rainfall. And at least the outcome when we know the impact of the El Nino with the variability, we will, for the ready nation to anticipate the next El Nino event will be coming for Indonesia. This is my research area in the Nino 3.4, and also we divide the Indonesia to 3 domains, western part for the domain 1, and the representative, the eastern and southern part, we call the domain 3, and the northern part we call as the domain 2. We use the sea surface temperature and subsurface temperature data, reanalysis wind for 850 millibar. And we use the 875 rainfall data observation, which we blended with the TRIPS data, satellite data. And here the area of the subsurface that we will see the evolution.
Mewujudkan Indonesia yang lebih mandiri bersama BMKG.
This is the research area, assess and at pattern and trend, and compare anomaly value, compare the period 97 to 2015, correlation analysis between SST anomaly, Nino 3.4, and also Indonesia rainfall anomaly. Here the comparison, the subsurface condition and also the sea surface condition in 97, between 97 with 2015, we see here that the strong or the warm temperature in the subsurface starting in May in 1997, but in 2015 the El Nino is coming starting yearly, starting on April, and move to the October, November to December. We compare that very strong El Nino and becoming the peak of the El Nino. It's quite similar that it will be peak in November and December, the intensity of the El Nino between 97 and also 2015. But unfortunately, we didn't see when the end of the El Nino, but because the limited of our presentation that could be uploaded in the ICTMAS, the end of the El Nino in 97 is in May 98, and the end of the El Nino 2015 is in May 2016. So there are different 1 month different that 2015 is longer than 97. Here the condition that we can see that in 82 for 14 months, 97 13 months, and 2015 and 16 14 months. This is the long period of the El Nino condition, and you see and on the table that starting in May and finish at April, and starting in May finishing in May 88, 98, and 2015 starting in April 15 and finish at May 16. And it is the condition of the HST in 3 domains that Indonesia has defined previously. In domain 1, we can see that mostly normal and warm condition for the HST condition in Indonesia, western part Indonesia, and the northern part Indonesia also neutral to warm condition in some area of the northern Indonesia, and also neutral to warm in eastern and southern part of Indonesia. It means that the condition of HST in Indonesia during the El Nino 2015 and is warmer than the 97. Now we check for the journal wind anomaly. We can see that during the El Nino that the westerly will be active in the Central Pacific, and it could be reached maximum when. And here we can see that the westerly active in 97, for westerly most 60 months, and for the 2015 also for 16 months. So not different period for the active of the westerly during this El Nino between 97 and 2015. And the interesting is here for the triangle green, that means the journal when the maximum could be reached, and the box, red box, that's mean for the SST anomaly could reach maximum anomaly, and a blue color for the subsurface maximum anomaly. We can see here, if we focusing on the 97 to 2015, this is the unique that the journal wind maximum, it come yearly before the SST go to maximum and also the subsurface. But in 2015, the maximum journal wind or the westerly maximum, it haven't yearly, but after that the maximum is reached by the subsurface condition, and then the next is the sea surface could reach the maximum.
Sorry, Mr. Adi, your time is 2 minutes left.
Okay. And another thing that we could see the condition in 2015 and 17 is the IOD. On 97, we know that the positive IOD also following the El Nino in 97, but in 2015-16, it could be mostly absent or neutral, or a little bit weak El Nino. We can see the comparison between the IOD is 97 compared with the 2015. So 97 is a really, really strong IOD condition, different with the 2015 only neutral, just reach a little bit weak IOD. And it is the result. We can see that 97 is a really, really safer condition for reducing rainfall in Indonesia, mostly, and get the wider that some area that get reducing rainfall. Different with 2015. 2015 is not full of Indonesia with reducing the rainfall. So this is a really, really very interesting question that why the 2015 even the strong El Nino, but not the give the safer impact like this 97 El Nino. So for the conclusion is El Nino 2015 had the highest anomaly with the 14-month period that it's mean the strongest El Nino event. We found that the shifting of the peak SST Nino 3.4 during the El Nino 15 and 16 with the starting earlier than 82, 83 or 97 to 98. Even though the 2015 and 16 is the strongest and the longest El Nino event, but in terms of impact, 97 and 98 has the wider effect on the reducing rainfall in Indonesia. We assume that it was due to the absence of the strong positive IOD during El Nino 2015, and also the condition of the EST around Indonesia during El Nino 2015 existing so warmer than 97 and 98 is also indicating more supporting condition for developing some convective over a maritime continent. So I think this my conclusion. In the future, we will be very interesting if we see or make the assessment for the impact of the global warming, reducing the impact of the El Nino at the maritime continent. Thank you, Mr. Chairman.
All right, thank you very much. That's a great presentation from Mr. Adi. And you can take on. Yeah, thank you very much. And now we can, before we move to the last presenter from the section 1, Mr. Harrison, you have a question from Adrian Matthews. You can prepare the answer and we will discuss it in the discussion sections. And for another audience, if you have any question, you can write it in the chat box. All right, so we can move to the third presenter. That is the last presenter from the section 1. Please welcome here from Leeds. That is Mr. Simon Pittman. Then is yours.
Hello, so hopefully you can see my slides.
Yeah, that's very clear. You can.
Okay, thank you. Yeah, so my talk is entitled Controls on the Variability of the Maritime Continent Diurnal Cycle and Mechanisms of Offshore Propagating Convection. So my first slide is just presenting an overview of the diurnal cycle of precipitation over the maritime continent region. So on the right-hand side, I have composites of precipitation from the TRIM product at 9 o'clock in the morning, local time, and then 6 p.m. local time. So you can see that in the afternoon and evening, we typically get the strongest precipitation over the islands of the maritime continent, whereas in the early morning, the islands are typically clear of rain, and that's when you get the strongest precipitation over the ocean. And you can also see there are regions where the precipitation tends to have propagated offshore overnight. So if you look at the top panel, you can see, for example, along the southwest coast of Sumatra or the northwest coast of Borneo, you can see reasonably strong regions of precipitation there where the convection has propagated offshore during the night. So what I've just described is the kind of classic view of the diurnal cycle, the kind of canonical diurnal cycle that we think of occurring regularly, but in fact it doesn't necessarily occur every day. And we know that it can vary depending on the large scale conditions. So previous papers have diagnosed this scale interaction. For example, in different phases of the MJO or ENSO, you will have perhaps the diurnal cycle of deep convection actually not triggering at all over the land, or at least the amplitude of that diurnal cycle being different, and also as equatorial waves propagate through the region. But the mechanisms, physical mechanisms of these scale interactions are not necessarily well understood. And so that's the subject of my talk, is to try to unpick the impact of these large-scale drivers on the local scale diurnal cycle, and to quantify the relative impacts of each of these drivers. So I started by looking not at the precipitation itself, but at the coastal winds, which we believe are relevant to the diurnal cycle, the sea breeze circulation in particular. So I've taken radiosonde observations from 2 field campaigns, one in November and December 2015, and one in November 2017 to January 2018. And we've used radiosonde data from Bengkulu, which is on Sumatra as shown on the map. And so those 108 days of the field campaign data, I took the 3-hourly radiosondes looking at just the zonal wind and used the k-means clustering algorithm to derive 3 different regimes of the daily winds. So if you look at the top panel here, these are the 3 clusters that came out of the algorithm. On the left, the one I called cluster 0. So you've got pressure on the vertical axis and time of day on the horizontal axis. So the one I called cluster 0 has strongly onshore winds all day. The middle one, cluster 1, has weak onshore winds all day. And then on the right, cluster 2 is predominantly offshore winds. Below the second row, I've just subtracted the respective daily mean from each of those. So you can see that you still see in the anomaly sense the land-sea breeze circulation that you'd expect. So why are these coastal wind regimes useful? Well, it turns out that if you look at the diurnal cycle of precipitation composited over each of those clusters, then you actually see quite a difference. So on the right here, sorry, I should say these are Hofmöller diagrams of precipitation taken over the thin red box shown on the map. So the x-axis on these plots is the long side of that red box, and then time is the vertical axis going downwards. So if you look at cluster 2 on the right, that's where you see the classic diurnal cycle. So when we had offshore winds, you get this deep convection being triggered over the high orography and then propagating offshore downwards to the left. Whereas over in cluster 0, we had the strong onshore winds. Actually, you don't get very intense precipitation over the land. There's no real sign to that offshore propagation, and the precipitation over the ocean is just dominated by what's going on the large scale. So if you understand, if you know which of these wind regimes you're in, then that determines which of the diurnal cycle of precipitation regimes you're in. So if we can understand how the large scale drivers affect the wind variability, then this gives us a physical link between those large scale drivers and the local scale precipitation. So what I've done here is I've just used 850 hectopascals as a representative level. So again, this is looking at zonal wind. These are time series now during those field campaign periods, where I've using, by identifying equatorial waves in a reanalysis data set and by regressing the wind onto MJO and ENSO indices, I can compute the U850 value that is associated with each of these large scale drivers. So the colored lines here are time series of the zonal wind at 850 hectopascals at Bengkulu associated with ENSO in the dark green, MJO in the dark blue, and so on for the equatorial waves. I've also drawn on the mean seasonal cycle as the dotted line. And if you add all of those together, you get the solid black line. And then the solid gray line is the total value from the reanalysis. So if these large scale drivers completely describe the wind variability, then those black and gray lines should match up. And for the most part, they do match up pretty accurately. The colored boxes then tell you which wind regime you're in. So for example, if you look at the first panel, you can see that we were mostly in cluster 2, that's offshore winds. That was with the strong diurnal cycle, but then there are a couple of days, the 26th and 27th of November, where you get a more onshore cluster. And that's, you can clearly see because of this dark pink line, that's an n=1 Rossby wave that came through the region. So you can see, and if you look through the other panels, I don't have time to talk through them all in detail, but you can see examples of where each of these large-scale drivers can push you into a different wind regime, which then therefore pushes you into a different regime of the diurnal cycle of precipitation. Now, that was just 108 days of data, so I have extended the analysis, this time using ERA 5 rather than the radiosondes. Again, computing the clusters, this time we found it was appropriate to derive 4 clusters, but they look broadly similar to the ones seen from the radiosondes. And if you run the same analysis and compare that black line and that grey line, the ones we said should match up, the histogram at the bottom is a histogram of the residual, so the absolute difference between the black and the grey. So if that's 0, then the large-scale drivers, as we've modelled there, the wind response to those drivers is a perfect predictor of the wind, and you can see that that histogram is indeed peaked towards 0. The orange curve here is the cumulative distribution, and I've drawn in red just as an indication the interannual standard deviation in the wind, and you can see that on 83% of days, you have the residual is less than 1 standard deviation. So I'd say that these large-scale drivers are indeed able to predict the wind regimes to a high degree of accuracy. So the question then becomes, okay, which of the large-scale drivers actually are the most important, and what phases of them are most important? So I've listed those for this southwest Sumatra coastline in the table at the top, and these schematic diagrams are then showing you which phases are important. So it turns out that the onshore wind regime, when you have a suppressed diurnal cycle of precipitation, that is associated with MJO phases 4 to 6, which provide an onshore wind direction. Also La Nina events will provide onshore wind. And when you're in the low pressure, the cyclonic phase of an equatorial Rossby wave. And so then you get more moderate precipitation over the ocean and some weak propagation onshore. The offshore wind regime, where you have the strong diurnal cycle indicated by the cumulonimbus cloud there and the strong propagation offshore, that tends to be associated with MJO phases 8, 1, 2, and 3, or El Nino events, or the high pressure anticyclonic phase of a Rossby wave. I also repeated this analysis for other coastlines in the maritime continent where we see the propagation happening. So northwest Borneo, for Java, and for the North New Guinea coastline. And I'm just going to finish with this summary slide, which then, having run the same analysis for all of these different coastlines, shows on the top row the large-scale drivers which are associated with onshore wind over that coast, and therefore that tends to give you a more suppressed diurnal cycle in most cases. And the bottom row, where you have the offshore wind regime, when you tend to have a stronger diurnal cycle. So for example, for Borneo, you see that the green arrow is no longer there, so ENSO doesn't have so much of an impact, but the MJO still does, with phases 5 to 7 giving you the onshore wind regime with a suppressed diurnal cycle, and MJO phases 1 to 4 giving you an offshore wind regime with a more active diurnal cycle and its offshore propagation. And then similarly for the other coastlines, we find that Rossby waves and westward mixed Rossby gravity waves tend to be important. Thank you very much.
All right, thank you very much, Mr. Your time is very good. So you finish the presentation in 10 minutes, Mr. Simon. And so we will move to the discussion section.
Discussion. Okay.
Yeah, we already have 2 questions here. So I will read the questions. The first one is from Adrian Matthews for Harrison, Mr. Harrison. So the question is, what were the MJO FMM bases during the days in CPEA 1 and CPEA 2? If you do the analysis based on the days in each RMM piece, rather than splitting just into CPEA 1 and 2, do the result change? That is the question from Mr. Adrian. And the next question is Ida Bagus, also for Mr. Harrison. The question is, can you explain about how do you determine the number of cloud layers in this study? Is there any certain heat swing for determining it? So we have two questions. Is there any question again from audience? You can just raise hand or on your speaker.
Okay.
Maybe Mr. Prof. Eddie, you have any question? Sorry, I think your speaker still mute, Mr. Prof. Eddie.
Yeah, I think we need consider time. We have only less than 6 minutes.
Oh yeah.
So it looks better if presenter answer the question coming from the audience.
Thank you very much. So, Mr. Harrison, can you please give a comment and answer about the questions? Time is yours, Mr. Harrison. Mr. Harrison, are you there? All right, yeah, you can answer the question from the audience. Time is yours.
Okay, moderator, thank you. And I will answer a question from Ida Bagus Gede Yamuna about explain how do you determine the number of growth layers in the study.
Yes, sir.
Okay, thank you for question. The number of layers was determined using the Zhang et al.'s methods 2018. So in simple, the is method use the relative humidity threshold value and each altitude as in the table above. Thank you.
All right, thank you very much, Mr. Harrison. So maybe you have any explanation about the Mr. Adrian Matthews questions? Maybe is that Miss Ida have any comment from the Harrison, Mr. Harrison answer, or is it enough, Miss Ida? Yeah, I think it's enough. For the Mr. Adrian. Oh, thank you very much. So it's enough from Mr. Ida. So we can move to the question from Mr. Matthew. Yeah, please. The time is yours, Mr. Harrison.
Yeah.
Apa bahasa MJLM sama? Sorry.
Okay. Is there any comment?
No,
Mr. Harrison? Mr. Harrison?
Okay. About question Adrian Matthew. I'm not yet analysis for day. I'm not analysis for day. And my research menggunakan indeks RMM maybe I don't explain in English. Maybe I went to Indonesia.
Yeah, it's all right. It's all right, Mr.
No. Maybe I can help you,
Yes.
Harrison. The question coming from Professor Adrian Matthews is how you can define this is active MGO and this is inactive MGO, because when we define active on inactive MGO, usually we use three parameters. First, amplitude, and the other one is the phase located in phase 2, phase 3, or phase 4 until phase 8. And the last one is from the duration of lifetime MGO, its phase itself. So the question is how you can determine MGO active and inactive phase in that time for both GPA1 and GPA2. That from
Okay, thank you, Mr. Edi Hermawan. Okay, the active MGO is determined based of the previous resurvey of its height is in the table above. Jadi menentukan indeks RMM aktif dan tidak aktif itu berdasarkan penelitian sebelumnya yang telah dilakukan oleh Nurzuki et al. Jadi penelitian ini melanjutkan penelitian sebelumnya, di mana penelitian sebelumnya telah mendapatkan fase aktif dan fase tidak aktif MGO. Namun penelitian sebelumnya fokus kepada struktur horizontal dari awan. Dan penelitian saya fokus terhadap struktur vertikal awan.
Iya, maksudnya, you can check at BOM Poama Australia that RMM1 and RM2 data, then you show in your slides, not directly just follow the previous study before this active and active. Maybe Professor Adrian wish you show us the data in that time. April to May 2004 and November to December 2005. Yeah, you can check.
Yes.
Yeah. It is just maybe some suggestions. Yeah, if you don't have that, you can check later and complete your study in the text your paper. Not right now.
All right, thank you very much, Prof. Edi Hermawan, for the explanation, and Mr. Hermawan for the answer. Sorry, Mr. Harrison.
No question to Simon Pittman.
Oh yeah, I think
Pittman, yeah. Oh,
I think
time is already finished.
Time is finished, but I think we will just move to another one, and if we have like more time, we will we will get the explanation. Yeah, the second one.
The second discussion.
Yeah.
Okay.
Thank you very much,
We
Mr.
understood.
Edi.
Okay.
And please welcome here. We have the Dr. Kunio Yoneyama is already here, I think. Yeah. Please welcome here Dr. Kunio Yoneyama as a convener. So you can hear me, Dr. Kuneyama?
Hey, right now, I just joined, so I'm sorry, I couldn't listen to any talks, so, but just join, so from now.
Thank you very much, it's all right. And I think in the end of this section, you can give like comment a brief comment for our presenters. Thank you very much for joining here. All right, so we will move to the section 2. So we have 4 presenters here. And the first one, we have Alif Nabila Roshida. So are you here, Arlif? Mr.
Yes,
Arlif.
thank you for the opportunity.
Oh, sorry,
Yes.
Miss Arlif. Yeah, sorry. Yeah, you can just start your presentation now. Your time is 10 minutes.
Please be careful.
Sorry, that's my bad. That's my bad.
I'm sorry, I don't have permission. Okay, I just got the permission to share the slide. So let me proceed to share it. I hope you can see it clearly.
Yeah, we can see it.
So good evening or good afternoon, I guess. My name is Arlif Nabila Rashida. I'm a student from Institute of Technology Bandung, Indonesia. So in this very occasion, I would like to share our study result entitled Influence of TBO-MJO connections on the turbulence variation in the TTL observed with equatorial atmosphere radar together with Dr. Nurjana Joko Trilaksono from ITD and Dr. Nur Sumadi. Okay, so in this presentation, it consists of 5 sections. So without any further, let's proceed to the first one. So as we know, atmosphere can be divided in layers. Near the Earth, we interact with troposphere, and above it, it's stratosphere. Every layer has its own characteristics and phenomena. And quasi-binary oscillation is one of stratospheric phenomena generated by vertical gravity wave activities. So in this phenomenon is defined by downward propagating solar wind with period of 28 months more or less. So in this figure, blue color means easterly phase and the bronze means westerly. During TBO easterly is associated with ascending motions. The tropopause is higher and colder. The vertical zonal wind shear across the tropopause is weaker, and upper tropospheric static stability is lower, and it's vice versa for TBO westerly. This indicates that TBO has a possible impact in other layers, especially troposphere. So in troposphere, we got MJO or Madden-Julian oscillation, the major fluctuation in tropical weather on weekly to monthly time scale. The MJO can be characterized as an eastward propagating pulse of cloud and rainfall near the equator with a cruise period of 40 until 50 days. So connections between the stratospheric quasi-binary oscillation and MJO has recently been found. MJO activities are significantly stronger in TBO easterly phase than westerly phase, but only in boreal winter, as shown in the right figure of past precipitations in phase 4 of MJO. So to get closer look on how TBO and MJO interact, a further study is required in troposphere and stratosphere boundary of equatorial region, or known as tropical tropopause layer. So we will talk more about tropical tropopause layer and how TBO and MJO interact. Here we see the vertical temperature profile. And with this figure, we can split the layers into troposphere and stratosphere. And TTL is a transition layer between troposphere and stratosphere, and by definition of high is in 14 until 18.5 kilometers. So in many ways, TTL acts as a gate to the stratosphere. In TBO easterly phase, observe more cirrus cloud in upper troposphere and will lower the insolation. That means weaker convective diurnal cycle. So the impact is stronger or more MJO days, and vice versa for TBO westerly. In this phenomenon, we see that the key factor is the state of TTL. Well, we know that one of important phenomena is in TTL is turbulence. Turbulence occur in TTL is responsible for vertical transport and of heat and materials within troposphere and stratosphere through mixings. So for analyzing turbulence in TBO and MJO connection, a longer data period and higher vertical resolutions are needed. So in this study, we use dataset from equatorial atmosphere radar. So the question is, are there any distinct variations in the turbulence intensity observed with air related to KBO MGO? To answer this, the question, we use spectral width to estimate turbulence intensity, where sigma turbulence or turbulence intensity nearly equal with spectral width observed from air minus sigma burdening effect, which can be obtained from multiplication of half power half with air, which is 1.7 degree, and horizontal wind. Note that the data used in this research is from the upward beam air to minimize the effect of the strong zonal wind shear. The second step is determining KBO from NOR is less than the limit. And the MGO day of log 0 is defined in phase 4, the first day of phase 4, where MGO, where air take place in West Sumatra, Agam, as seen in this picture. And then we select MGO phenomena just in extended boreal winter. We found 46 MGO cases with 17 cases in KBO easterly and 18 cases in KBO westerly. So the first result is a composite figure of all MGO in all KBO phase to analyze the state before and after MGO. We take 15 days data after and before MGO. So the turbulence intensity seems to increase 0.1 until 0.2 meter per second after MGO. The turbulence itself can be generated from dynamic instability, which is from shear, and thermodynamic instability, which, for example, from convective instability. To examine the mechanism, we look at zonal wind and the vertical wind. Zonal wind strengthen after MGO and lasts for 10 days. The enhancement of vertical wind also observed for 4 until 8 centimeters per second after MGO. With this, we can conclude that there is enhancement of updraft or vertical motions. So in this slide, we will focus on the difference between KBO easterly and KBO westerly for zonal wind, turbulence intensity, and the convective activities. In KBO easterly, we can clearly see the turbulence intensity and zonal wind are stronger after MGO passing through air. An interesting pattern observed in KBO westerly, while turbulence intensity in 12 until 14 kilometers and 16 kilometers are way equally more stronger before or after MGO. We are still not sure why this pattern arises, but we suspect this is due to impact of stronger local circulations. And the next question is, what mechanism generated turbulence in TTL? This bottom figure, our precipitation, showed with blue lines, and OLR showed with red lines. The data obtained from wind value throughout 5 north until 5 south, and 97.5 until 102.5 east. In KBO easterly, we observe the precipitation peak just before MGO passing to air. So we conclude that the turbulence in TTL is in KBO easterly phase is mainly generated from convective instability. The next is to take closer look on the difference between KBO easterly and KBO westerly. We present the difference between the two phases of turbulence intensity and vertical wind. Although in previous figure, we see that there is equally stronger turbulence in KBO westerly.
Yeah, your time is 2 minutes, Ms. Alif. Sorry about that.
Thank you. In the figure, we know that there is more turbulence with value 0.1 until 0.3 meter per second observed at 16.5 until 18 kilometers, and associated with vertical wind strengthened in KBO easterly after MGO passing through air. This is due to more updraft seen in vertical wind difference and stronger tropospheric jet convections. So to sum up, we have conducted an analysis on the turbulence variation related to QB-on-J connection. We have estimated turbulence intensity using spectral data obtained from air throughout 2001 until 2019. This enhancement of turbulent intensity was observed during NGO and QBO easily phase, along with an enhancement of zonal wind and updraft shown in strengthening of vertical wind. This enhancement presumed to be associated with stronger convective and precipitation system before the NGO that caused by a more unstable atmosphere in QBO easily. But still, the generation mechanism needs to be studied further. So that's all for our presentation. Thank you very much.
Wow, thank you very much. That's really nice presentation. And all right, so we will move to the next speaker. And again, remembering for the audience, should you have any questions, you can just write the questions in the chat box here.
Okay.
Yeah, we will move to Rigita. Are you here, Rigita? Have you already here, Miss Rigita?
Yeah.
Yeah,
Hello?
you can. All right, thank you. You can start the presentation and your time is 10 minutes.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
I explain my research with entitled Analysis of Vortex Development over Eastern Indian Ocean using Potential Verticity. That lower level vortex formation is associated.
Oh, sorry, Rigita, can you please do slideshow your presentation, please?
Indonesian geographic location causes the region to have many phenomena.
Sorry for interrupt your presentation, Rigita. Can you please slideshow your presentation? Are you have already that to slideshow?
I have already to slideshow my presentation, but
right.
yeah, maybe my connection.
No. Your connection is fine. Just looks. I think you can just continue your presentations. That's
okay.
like yeah.
Indonesian geographic location causes the region to have many phenomena. The phenomena that is quite significant influence on wind circulation in Indonesia is a vortex event. One of the low vortex phenomena that is often studied in Indonesia is the Borneo vortex. Meanwhile, there is a low level vortex whose occurrence frequency is quite significant compared to other areas in the Indonesian maritime continent, namely the vortex in the Eastern Indian Ocean. This vortex serves as one of contributing factors for flooding events at Jakarta and plays a role in the development of tropical cyclone in the Indian Ocean. Hence, both formation and development of this vortex is very important to study. The low level vortex formation is associated with blocking by topographical feature. An effect of verticity anomalies in the upper troposphere that moves towards the surface or vice versa. Analysis of formation mechanisms and characteristics of this vortex can be explained by potential verticity. The analysis of potential verticity is quite widely practiced at present to study atmospheric phenomena such as the diagnosis of cyclonic development and movement. Therefore, further analysis will be made regarding the characteristics of the emergence of vortices over Eastern Indian Ocean, as well as analysis of the evolution and strength of the vortices through potential verticity parameter based on the characteristics obtained. The data used in the study is ICMWF area intermediate analysis data for 18 DGF period data. The zonal wind and meridional wind data were used for vortex identification. Meanwhile, the zonal wind, meridional, and temperature data were used to calculate the potential vorticity. And SST data were also used for further analysis. A vortex is identified by following the study by Chang et al. Vortex identification study area with coordinates as the shown on figure. After determining the vortex using a streamline, the relative vortex value will also be analyzed on the day when the vortex was identified in the previous method to increase objectivity in the identification of phenomena. The calculation of potential vorticity refers to a following equation, where the PV is the potential vorticity of isentropic coordinate. The potential vorticity were calculated at isentropic level, while the data used are pressure level data, so that each component must be interpolated in isentropic level first. The interpolation method used is linear interpolation. Based on Haskin, the concept of potential vorticity anomalies can connect connecting upper level and lower level. Upper level in the tropic is the same middle troposphere. It's about 500 hectopascal or about 328 Kelvin in isentropic layer. And lower level is where the phenomenon was identified is 925 hectopascal or about 302 Kelvin in isentropic layer. And the result shows that frequency of occurrence in each year was different. The vortex identification process results in a total of 84 vortex system occurrence in 295 days during the period of analysis. The average lifespan of a vortex system that occur range from 1 until 11 days with 3 patterns of vortex direction of motion: stationary, moving west, and moving east. A stationary vortex tend to have a relative shorter lifespan that the vortex move eastward or westward. And this figure shows the spatial dispersion of the 84 vortex system over Eastern Indian Ocean. After obtaining the characteristic of the vortex movement, then it will be analyzed through composite potential vortex analysis of vortex evolution. Analysis of the composite potential vortex anomalous value will be carried out to see the beginning of the formation of the cyclonic pattern on this vortex system. In the composite of potential vortex anomalous, it was seen that a few days before the event, there were strong negative anomalies of potential vorticity in south and in west. 3 days before the event, the negative anomalies from the west began to move eastward. Negative anomaly of potential vorticity got stronger and formed a cyclonic pattern that began to appear on the second day before the event. This suggests that there is a negative potential vorticity. Anomalous affection from the west remains connected to the vortex system and amplifies the formation of its cyclonic pattern. The existence of a negative affection of potential vorticity from the west, which is getting stronger, is also showing the cyclonic pattern, which is further identified as the vortex. On the following date, it was seen that the center of the vortex is moving westward. It's about 200 kilometers from zero distance of vortex was formed. And the composite evolution of vortex event move eastward has the same mechanism as the vortex move westward. On the day of the event, maximum negative potential vorticity anomalies with a full cyclonic pattern has appeared in a center of the domain, about 0 kilometer distance. The wind pattern also shows a cyclonic pattern. On the second day of formation of the vortex, shown in this figure, the vortex center will move eastward. Then the evolution of stationary vortex is also same as other vortex. On the second day of formation, the vortex, which is shown in this figure, the center of the vortex doesn't change, which indicate the vortex is stationary. The potential vorticity anomalies can form either at upper level or lower level or vice versa. A negative potential vorticity anomalies at the lower level tend to be stronger than the upper level. So that the anomaly at the lower level is likely to affect the anomaly at the upper level. This shows that the event of vortex over Eastern Indian Ocean originated from the attraction of negative potential vorticity anomalies from the west. The cyclonic pattern that was formed was not due to the influence of the negative potential vorticity from upper level.
Your time is 2 minutes left, Ms. Regita. Sorry about that.
The negative anomaly values of stationary vortex tend to be weaker, and on the second day and third day of the vortex event, the vortex system is no longer connected with a negative potential vorticity from the west. Then the vertical plot also shows that on the vortex westward, eastward, westward is still connected with negative potential vorticity from the west. So that the moving vortex system is getting stronger due to the strengthening of the negative potential vorticity, which causes the vortex system lifespan to be longer than the stationary vortex. And in this discussion, analyze the movement of vortex. It can be seen that the evolution of the vortex movement on the first day, second day, and the third day of vortex shows that the vortex tend to move toward the positive SST anomalies. In the previous research, suspect that the vortex as a trigger for flooding in Jakarta. We try to analyze based on potential vorticity. The negative anomaly starts to strengthen until it forms a cyclonic pattern on 31st January, which was indicated as the initial formation of vortex. Maximum anomaly value occurred in 1st February. Negative potential vorticity anomaly in the vortex system, we can see that not directly related to potential negative vorticity anomalies over Jakarta. Vortex move westward and away from the Java region with the time. Potential vorticity anomalies can be generated by interaction with topographical feature. Based on the analysis of potential vorticity shown in the figure, the atmospheric instability in the Jakarta area may be related to an increase in meridional wind from the north, which interact with the topographical feature of Jakarta, not due to the vortex system in the Eastern Indian Ocean. Based on the identification of vortex event, it was found that the vortex in Eastern Indian Ocean tend to move. There are 3 characteristics of the vortex movement. From the analysis of potential vorticity anomalies on each characteristic of vortex movement, it shows that the vortex event is associated with negative potential vorticity anomalies from the west and is affected eastward. The attraction of negative potential vorticity anomalies from the west causes the formation of negative potential vorticity anomalies, and strengthening of the anomalies become increasingly negative to form a cyclonic pattern, which is subsequently identified as vortex. Thank you.
All right, thank you very much, Ms. Regita, for the presentations. That's really good. And for saving the time, we will move to the next one on the next presenter. But before that, Ms. Arlif, you have a question from Mr. Adrian Matthews, and you can prepare the answer. All right, so we will move to the next presenter from ITB, Firas Rashad, Mr. Firas Rashad.
Yes.
All right, thank you very much. You can now start the
May I share my presentation?
Your presentation is still not.
I'm sorry, my PC is stuck.
Oh, that's yeah.
I'm sorry. It may be some seconds, something.
Okay.
Okay. Yes, I can move my cursor now.
All right, nice. Yeah, you can start the presentation.
Okay, thank you very much. Okay, good afternoon, everyone. My name is Firas Rashad, and today I will present you about our study, short vertical wavelength gravity wave activities in the upper troposphere, lower stratosphere, observed with global navigation satellite system radio occultation under different QBO phases. So quasi-binaural oscillation, or QBO, is a zonal wind oscillation in equatorial stratosphere with mean period in 28 months. The main driver of QBO is produced in the troposphere, which is the gravity waves. In illustration from convection, we can see in this left figure, there are upward propagation waves with eastward and westward propagation into the stratosphere. This gravity wave has a role in transporting momentum to the stratosphere region. Then in the stratosphere, gravity wave will interact with mean flow, become oscillation, which called quasi-binaural oscillation, or QBO. And the change on the gravity wave source in equator, or the change on convective activity, can affect the quasi-binaural oscillation propagation or the period. One phenomena can affect QBO is El Nino Southern Oscillation, or ENSO. While El Nino, change of convection distribution and tropospheric circulation leads to shorter QBO periods. That's the result from the previous studies. So our motivation of this study is observation of short vertical wavelength gravity waves are still limited. So are there actually distinct characteristics of gravity wave activities during longer and shorter QBO? Obviously, from observation data from GNSSRO. The Global Navigation Satellite System radio occultation, or GNSSRO, is the data that we use in the study to determine the gravity wave activity. We use data from cosmic satellite that reconstructed using FSI method. This cosmic FSI data provide temperature up to 30 kilometer height with vertical resolution 0.1 kilometer. The second data that we use in study is from MERA2 reanalysis, zonal wind in 50 hectopascal for the September 2006 until December 2015. I'm sorry, it might be my connection is unstable. Yes, I'm sorry for if my present is very bad. It's bad. And then the study area is from 10 north until 10 south, as we can see in this figure. And in the study, we define gravity wave activity by zonal mean gravity wave potential energy derived from temperature profile from observed GNSSRO. And this is the comparison of FSI retrieval method and the other method. So the first result of the study is individual profile of wave number spectrum of temperature perturbation. The most left figure is temperature in upper troposphere, lower stratosphere, 20 until 27 kilometer. And the second left is the temperature perturbation, the difference between the profile and the mean profile daily. And from this temperature perturbation, we employ fast Fourier transform, or FFT, to obtain wave number spectrum of gravity wave. This is the energy density versus wave number diagram. And from this diagram, we can see the highest energy density is in low wave number. But for higher wave number, we can see that the energy density value of gravity wave is has similar value or even more value than saturated gravity wave spectrum. And from this energy density, we calculate the energy content. And we have noted that minimum of vertical wavelength of the real atmospheric signal from cosmic FSH and SSRO data is 500 meters. So we define gravity wave from 500 meter vertical wavelength and higher. So after this, we calculate the zonal mean potential. The with number. And then we have a result of a zonal mean potential energy compared to the QBO index. This is and in this top figure we define gravity wave by 3 wavelength categories. The green line is for 0.5 until 3.5 kilometer wavelength, and the blue line is 0.5 until 1 kilometer wavelength or less than 1 kilometer wavelength. This blue lines, and the yellow lines is the difference between them. However, the time series pattern of the gravity potential energy in all wavelengths are relatively similar. All potential energy value reach its peak value in QBO transition, which means there is gravity wave potential energy enhancement during the QBO transition period. And with the peak value of 0.5 until 3.5 kilometer, around 8 joule per kilogram, with a minimum value about 5 joule per kilogram, and for the less than 1 kilometer can reach until 3 joule per kilogram, and the minimum value is about less than 2 joule per kilogram. And then after this, we will focus our analysis about of these blue lines, this less than 1 kilometer, but not just this blue lines. We divide these blue lines with the green lines to find the short vertical wavelength ratio of the all spectrum. The result is in the bottom figure. The pattern of gravity with less than 1 kilometer ratio, this bottom figure is still associated with the QBO index. Still same with the previous figure, their enhancement of short vertical wavelength activity value during transition period. But there's a different higher value of the ratio is occurred during westerly to easterly QBO period and lower during easterly to westerly QBO period, about 0.44 and 0.42. Then the ratio value gradually increase while westerly QBO period. Then to get more analysis of this short gravity wave activities, we make the time exception of this variable, but this time exception is the figure. This time exception is calculated using FFT or Hayek interval. So, for example, in different between the previous figure, which is the 7 kilometer. For example, 22 kilometer needs 21 until 23 kilometer temperature profile. Then and this figure use 30 days of moving average. The most clear pattern is there's downward propagation of energy of short vertical wavelength gravity ratio during the QBO transition. And still, there is some more enhancement during the westerly to easterly QBO period than during the easterly to QBO period. Easterly to westerly QBO period with a similar value to the previous figure. And on the other hand, we can see there also like there is also a small upward propagation of this short vertical wavelength percentage value, or the ratio, or the short vertical wavelength activity, while the westerly QBO period, only during westerly QBO period. Then the intersect of the upward and downward propagation of this ratio occurred during westerly QBO maximum zonal wind. Then the zonal wind amplitude after that will continuously decrease, means the intersect being changed to the QBO phases. Additionally, we can see at 2010 there is a clear pattern here that easterly QBO period is extremely short compared to the other. Related to that, from this time extraction, we can see there's a strong enhancement of the short vertical wavelength activity before the easterly QBO period. Then there is an enhancement and can stay longer. And while easterly QBO period, potential energy percentage value relatively low, above 22 kilometer. The one argument about this is related to ENSO, because starting 2010,
sorry,
on index.
Your time is 2 minutes left. Sorry about that, Mr.
Okay, thank you. Because starting indicate El Nino, and we can see in the whole time series that only index or ENSO is correlated with this short vertical wavelength activities in UTLS. More short wave while El Nino than La Nina. After all, we can make summary that gravity wave potential energy is in association with QBO phase, and found that gravity wave energy enhancement around QBO transition. And the ratio of energy for wavelength less than 1 kilometer to the total is higher during westerly to easterly QBO than easterly to westerly QBO transition. And in addition, we have shown that the of gravity of potential energy is some.
All right, thank you, Mr. Frilas, for your presentations. We have finished from the presentation of Mr. Frilas, and so to overcoming the time, we will just move to the next question. Next presenter from Ms. Devi Fatmashari, that is from BMKG. So, Ms. Devi, you can start your presentation now.
Okay, thank you.
Yes.
Can you see my presentation?
Yeah, we can see it.
All right. So, good afternoon, everyone. Today, I would like to present my study about the regional Hadley cells response to the sea surface temperature distribution across the Indo-Pacific Ocean. So Indonesia is located in between Pacific and Indian Ocean. So that is why the major climate variabilities that influence Indonesia are ENSO in Pacific Ocean and IAD in Indian Ocean. However, for this study, I only focus to the Pacific Ocean or the SST distribution across the Pacific Ocean. So the occurrence of, so ENSO has two opposite phases. There are El Nino and La Nina. During the occurrence of El Nino, the warm SST across the Indian Ocean shift to the Eastern Pacific, and the shifting of the sea surface temperature across the Pacific Ocean could influence the atmospheric circulation above this region. And one of the tropical atmospheric circulation is the Hadley cells. For the global average cells, Hadley cells has an upward motion in the tropics and flows to the pole in the upper troposphere and sinking in the subtropics and flows back to the tropics in the lower troposphere. However, the strength of the cells are not always the same in some region. The study from Timan Wells 2003 shows that Hadley cells are very sensitive to the heat distribution. They shows that during the solstitial season or during the winter and summer season, Hadley cells are not equally strong in the two hemispheres. It is due to the meridional temperature gradient. So in the winter hemisphere, the regional cells over this region are stronger than the regional cells over the summer hemisphere, because the temperature gradient in the winter hemisphere are stronger than the meridional temperature in the summer hemisphere. And this background condition raises the research question and the purposes of this study, which is to investigate the regional Hadley cells strength in relation to the sea surface temperature distribution in Pacific Ocean, and also to investigate the rainfall pattern distribution in Indonesia related to the Hadley cell strength anomaly. And then these are data sets that I use. I use NINO 3.4 index as ENSO index, and then I also use sea surface temperature, vertical velocity, marginal wind, and also monthly rainfall. So the events selected in this study are pure ENSO events, which means there's no contribution or there's no relation with the IOD event in the other ocean. So these are the year of the pure ENSO event. And then I also found the relation between Hadley cells and ENSO before starting the study. I also use composite analysis to investigate the SST distribution across the Pacific Ocean during ENSO. And this analysis aims to know how the heat sources in the equatorial ocean shift, because this background condition will influence the behavior of the cells, since the Hadley cells is thermally driven cells. Also use composite analysis to analyze the strength of the regional Hadley cells, and also to examine the rainfall response in Indonesia to each event occurrence. And this is the SST anomaly during ENSO. From this picture, you can see that during the occurrence of El Nino, Indonesia has negative SST anomaly, while the Eastern and the Central Pacific Ocean, they have positive SST anomaly. In contrast, during La Nina, Indonesia has positive SST anomaly, while the Eastern Pacific has negative SST anomaly. From this picture, you can also see that Indonesia and Eastern Pacific, they have opposite SST polarity, and this background condition could lead to opposite response of regional Hadley cells, because these cells are very sensitive to the heat distribution. And the next is about the correlation between vertical velocity and sea surface temperature in NINO 3.4 domain. From these results, we can see that Indonesia has negative correlation with the NINO 3.4 domain, while the Eastern Pacific, they have positive correlation with the NINO 3.4 domain. And the research from 2004 also support this result. He states that there is negative correlation between Eastern Pacific's regional Hadley cells and Walker circulation. And there's also positive correlation between Western Pacific's regional Hadley cells and Walker circulation. This means that when the Eastern Pacific warms up, the Walker circulation is weaker than the regional Hadley cells over Indonesia, or the Western Pacific is strengthened. In contrast, when the Indonesian waters warms up, the Walker circulation stronger and the regional cells over Indonesia is getting stronger. And the next to get the real results from the vertical velocity, here is the vertical velocity anomaly. I use vertical velocity because vertical velocity shows upward and the downward motion in the atmosphere. It means that the more upward motion in the atmosphere, the more convective activity in that region, and the stronger the regional Hadley cells over that region. And from these results, we can see that during the occurrence of El Nino, Indonesia shows a negative vertical velocity anomaly. It means that when the Eastern Pacific warms up, Indonesia has a lower vertical velocity value than the normal year. This means that the regional cells over Indonesia is getting weaker. In contrast, during the occurrence of La Nina, Indonesia has more positive vertical velocity. It means that the regional cells over Indonesia is strengthened, and the regional cells over the Eastern Pacific is weaker, because in the Eastern Pacific, they has negative vertical velocity anomaly. And the opposite response of regional Hadley cells over the Western and the Eastern Pacific is due to the difference in the meridional SST gradient and also the energy source over the region. The shifting of the warm SST to the Eastern Pacific during El Nino causes the east-west SST gradient in the equator weaken, which also lead to the meridional SST gradient in the Western Pacific weakened because the SST in the Western Pacific is cools down. And when the meridional SST weaken, the pressure gradient also weaken, thus leads to a weakening of the regional Hartley circulation over the Western Pacific Ocean. And I also noticed that the anomalous Hartley cells strength depend on the anomalous strength of SST. It means that when the sea surface temperature anomaly reach its maximum anomaly during the major phase of ENSO, this means that the regional Hartley cells anomaly also reached its peak during the major phase of ENSO. And the last...
Yeah, your time is 2 minutes, Ms. Davis. Sorry about that.
Okay, thank you. And the last is the precipitation response. We can see here during El Nino, most of Indonesian region get negative response, while during La Nina, most of Indonesia region get positive rainfall response. And this means that the strength of regional Hartley circulation is affecting the convective activity in Indonesia. And since the energy in the Western Pacific is decreased due to the warm SST shifting to the Eastern Pacific during El Nino, the convective activity in this region is suppressed and results in reduction in precipitation in Western Pacific. And the suppression of the convective activity over the Western Pacific is in agreement with the weakening of the regional Hartley circulation over this region. And this is the conclusions of my study. SST variability over the tropical Pacific is affecting the meridional circulation. The anomalous strength of the regional Hartley cells depend on anomalous variation of SST. And during La Nina, the regional Hartley cells over Indonesia is stronger and enhanced convective activity in Indonesia. In the other hand, during El Nino, the regional Hartley cells over Indonesia is weaker and suppress the convective activity in Indonesia. And that's all from my study. Thank you for the attention.
All right, thank you very much, Ms. Devi, for the great presentation here. So we will just move to the next section. That is a discussion. So we have total 8 minutes and we have 2 questions here. The first one is for, I think, Mr. Alif. That is from Mr. Adrian Matthews. For the question is there are further impact to the work? Can the enhanced turbulence observed since during MJO and UBOE lead to a change, acceleration or decelerations in the zonal winds at that level 16 km and therefore impact on the development of the QPO? Yeah, this is the question from Mr. Andrew Matthews, and that's also just answered in the chat below. But if you have some comment or explanation about that, you can just explain it. And the second one is for Ms. Rigita from Dr. Kunio. The question is, this may not be a main point of your study, but I wonder you see any topographic barrier effect from Sumatra high mountain from PV viewpoint when they enter MC regions. So please, Ms. Alif, if you have any explanation, any comment about that, you can just start it.
Yes, thank you, Mr. Matthew, for the comment. I think it's already clear by Mr. Nur Sumadi. Yes, that is our next agenda to further examine the feedback effect of sonar wind using this data set. I think that's all for me. Thank you.
Very much. So we just move to the next questions. Ms. Rigita, you can just give the comment about the question or the answer for the question. Please, your time.
Okay, thank you for Mr. Kurnia Yonetama for the question. The first, to explain this question, we didn't further analyze to emerge of PV due to topographic effect, but in distribution in figure that show distribution vortex, we know that the vortex which is close to the topography of Sumatra. Okay. In this figure, we can see that the vortex, which is close to the topography of Sumatra, and I suspect that the western disturbance associated with the negative anomaly of potential vorticity and relate to the equatorial westward that blocked by topographical feature. Okay.
Yeah,
maybe.
thank you.
Yes, thank you so much. Because when we look at the PV diagram, we always aware for the such interaction between the such a barrier, because in the viewpoint of the conservation of the PV, they detour before entering to the such a high mountain. So I think I guess some feature is different from when they close to the mountain area or not. So that is the reason why I asked. But yeah, thank you.
Yeah, thank you very much for the explanation, and Mr. Kunio for the feedback from the presenter. And I just wondering, the time is up, so I think we have to finish these discussions, and we will move to the conference. And yeah, we have.
Okay.
For the first one, we will give the time allocation for Prof. Eddie to give like a comment or feedback.
I think first coming from Dr. Yoneyama.
Oh,
yeah, we have two conveners here. So I would like to give firstly to Dr. Yoneyama, Kunio Yoneyama. Please. Thank you.
Thank you very much, please, Dr. Kunio Yoneyama. Time is yours.
I'm sorry, I speak up, but yeah, today I could hear the good talk, and besides, basically I'm really impressed with the some guys really analyze the very new technique and new approaches. But I think today, of course, you only show your result. But I wonder if you really, especially for young guys, especially if you study more, I think I strongly recommend you that you read many papers, because recently over this maritime continent region, there are many papers. For example, the MGO and the QBO connection is very one of the hot topics. So I think you will find many papers. Of course, you've already read them, but I strongly recommend read more, because even from such a published paper, you can find a new something to hint to enhance your research more. So I think I strongly recommend you to read more. And also some guy, I forget his name, but for example, the GNS calculation is one of the, of course, the very important research tools. So I think I strongly encourage, and I want to see your further results more. So anyway, I could enjoy much about our presentation. Thank you so much.
Thank you very much, Dr. Kunio Yoneyama. Now, please, Prof. Edith, please your turn.
Okay, thank you very much for my opportunity. First, I found here from 7 presenters, 2 people talking about the ER data, equatorial atmosphere radar data. They are Horizon, Prima Donna, and Nabiratul Rashida. But Horizon Prima Donna use the very old data, 2004 and 2005. My suggestion is please try to use the new data, not old data. Maybe it is very important to analyze. But my suggestions, another suggestion is, please be careful when you select when MGO active and inactive phase, because it is very important. The first one more thing is important is please try to explain why cloud vertical structure is very important to be investigated. it is some suggestion to the first presenter, Horizon Primadonna from Andhras University. The second about our Adi Ripaldi, very nice presentation. You mentioned that impact of El Nino event 2015 stronger than 1997. My suggestion is please check the IOD the IOD value in that time. And also from Simon Pittman from UK, it is very important study, but unfortunately he studied only Bengkulu. We need more location to check the offshore propagating convection in that time. Not only one case, but many cases, maybe it's better. For example, maybe tropical cyclone should be checked in that time. And then coming to the next presenter. Oh yeah, I think it's better if Dr. Pittman try to focus impact of diurnal cycle, not only from MGO, equatorial waves, and so, but also to Indonesian rainfall monsoonal, anti-monsoonal, and equatorial tape. The offshores and onshore is also very, very important study. The fourth presenter, it is very, very nice presenter, presented by Arif Nabilatul Rashida from ITB, talking about KBO, MGO. Yeah, the first question is, please be careful when you determine turbulence estimation coming from the air. I think we need to consider not coming from among the spectral width, but please try to check how you can derive that formula. The other one is MGO. Please be careful. Usually MGO active during ASEAN winter season and active maybe summer. You cannot use on time without sparingly, because your data is very, very longer, 2001 until 2019. The next is because you use only one single location and data every 10 minutes, please make sure in that time MGO passing over Koto Tabang. And also strong KBO usually located at 1000 hectopascal. It is far away from the topical tropopause layer, so we need to consider about it. The next presenter is Ringgita, talking about vortex and potential vorticity. I think you need more study cases. Please select the location and time, and also impact of potential vorticity on the Indonesian rainfall anomalies. And the presenter number 6, Firas ITB, talking about the KBO, talking about still similar with the Arif, because talking about near to tropical tropopause layer also. Please be careful when you explain the mechanism KBO. It's located strongly 10 hectopascal and so in the surface. So mechanism should be made clearly. And the last one from Devi, BMKG, talking about ENSO, especially Nino 3.4. Unfortunately, in your conclusion, you don't mention about the vertical velocity at 500 hectopascal. Why? You select 5 hectopascal. Why not in surface? Why not another layer? And please try to make more cases, and maybe the possibility of vertical velocity for monitoring or for predicting the big anomalies, especially rainfall over Indonesia. I think since some suggestion is like this.
Hello. Can I have a comment?
Yeah.
Yeah, regarding your comment about the estimation of turbulence using EAR data, we are cite the paper wrote by Professor Soichiro Fukao in 1994, and then paper from Nostrom, and also paper by Dr. Masatomo Fujiwara.
Yeah.
So I think you may read those papers that state or explain how to estimate turbulence intensity using EAR or using a very high frequency radar. Okay, thank you.
I know that because pre-Ultra, Foucault, Nastrom, etc., they don't use the ear data. They use another radar data. Then they already use another. I don't remember. They use the some a little constant or another.
Dr. Masatomo Fujiwara used EAR data.
Oh, I see. Okay, we will check again. Yeah. Anyway, whatever you done is very good, very excellent. I hope what I have mentioned here just to make sure how the estimation turbulence is already estimated already done using the formula. I mentioned like this because I a bit wonder when Fujiwara. Yeah, I mean that we will check again the formula. Okay, thank you very much for your response, Dr. Nursomadi. I think on more have more than 10 minutes what I have mentioned here. Time back to the moderator.
Thank you very much for Prof. Eddie and Dr. Kunio Yoneyama. That's very clear and good comments for improving the quality of our researcher here from the presenters. And thank you very much for the audience. That's very active discussion here. And unfortunately, we have to finish these sections. But before that, please turn on your camera for your audience, presenter, and all. So we will take some picture from the documentation here. Just a minute. Wait a minute. So.
Big, not ready yet too. 1 minute for preparation.
Aduh, Prof. Edi kayak dulu mau nyisir kayaknya.
Yeah, no worries about that. Okay, I will try to. Thank you very much, Emma Howard, and another one. You can turn on the camera, please. All right, we will take some photo shoot here. 1, 2, 3. Now another slides. 1, 2, 3. Great, thank you very much. You are very nice, guys. And thanks. And yeah, we have to end this meeting. Thank you very much for your participation here. And we will end the meeting now. And from the section, it's finished, and we will meet tomorrow for the third day of the ICTMAS seminar. Thank you very much. Have a nice day, and see you tomorrow, guys. See you later.
Thank you.
Thank you for leading this discussion. Thank you.
Yeah,
See you.
Really appreciate that. Thank you very much.
Waduh, tadi apa nih? Oh, wah, daya.
Sorry.